Hello statistics students, my name is Emigh, and this video will start our discussion on Chapter 5, Probability Distributions. Section 5.1 title, Probability Distributions. Definition: probability distributions, a description that gives the probability for each value of the random variable, typically x. Let's look at an example of a probability distribution table. First column is titled Mexican American jurors, and here we have a count of exactly how many Mexican American jurors there could be on a jury which has 12 members. So there could be 0. Probability is pretty low though, referring to the second column now, which is the corresponding probability. Probability that there are 0 Mexican Americans on a jury, 0.00. Same for 1, 2, 3, 4 creeps up a little bit with probability, 5, 6 a little, 7 a bit more. If you're thinking about this as percentages, this would be about 6% of juries have exactly 7 Mexican American jurors on them. And we see the probability increasing, 0.13, 0.22. Looks like this one's the highest, 0.29 is the probability of randomly selecting one jury and there being exactly 10 Mexican Americans on that jury. 11 drops a little bit, 0.19, and the probability of all 12 jurors being Mexican American on a randomly selected jury is 0.07. We can take this information here from the distribution table and put it into a probability histogram. So we can see here on the x-axis or the horizontal axis, these are the counts for the number of Mexican American jurors on the jury and the height of each of the bars. The higher it is, the greater the probability of randomly selecting one jury and it having that many Mexican Americans on it. To have a true probability distribution, 3 requirements have to be met. Requirement number 1 is that there has to be a numerical random variable x, and its values are associated with corresponding probabilities. And that is definitely the situation we have here. Our first column represents the random variables. These are the x's. And it covers all possibilities, 0 to 12, and each one has a corresponding probability. So that right there, corresponding probability. Second column is all the corresponding probabilities, which would be noted as the probability of x. Okay, so first requirement is met. Second requirement is that all the probabilities have to sum to 1. So if you add all these up in your calculator, you need to get 1. We're very, very close to it because these may have been rounded off. We should be super close to 1. I like to think of this as a percentage. If this is a true probability distribution, then these probabilities right here would have to add up to 100% of all possible outcomes. So that's where the 100% is the same as probability of 1. Okay, so if we add those up, we will get 1. So second requirement is met. Third requirement is that each probability value must be between 0 and 1. That is true for all probabilities. So just looking at ours quickly, yep, those are all decimals between 0 and 1. So ours meets all 3 requirements. So we definitely have a probability distribution here with this data. Let's use an example where we're asked to find the mean, variance, standard deviation, and expected value of a probability distribution. For this example, though, we're going to be talking about the number of tails, so that's going to be the x, in 2 coin tosses. So to set up our table, we need all of our possible x values. That would be all the possible times you could get tails, or how many counts you would get tails if you flip a coin twice. So you could get tails 0, 1, or 2 times in those 2 coin tosses. And each of the corresponding probabilities will go here. So I'm going to quickly write up a sample space of if I were to flip a coin twice, I could get tails then tails. That would be this 2 right here. I could get heads and then tails. That would go for the 1 outcome of tails. I could flip a coin and get tails, flip it again and get heads. That would also count as an outcome of 1 heads. Or, last option, I could flip a coin twice and get heads both times. So this gives us a sample space or a total of 4 possible outcomes. How many in here have 0 times in which tails was the result of the coin flip? Just right here, heads then heads. So 1 out of 4 is the probability that we will flip the coin twice and get heads and get tails 0 times. I should write tails here so it sticks in my head more. Tails is the count of tails, and that's just per the questions directions. Okay, 1 tails here and here, so 2 possible out of the 4 would give us exactly 1 result of tails. And then 2 tails, that's the first one. There is 1 out of our 4 in our sample space. That results in exactly 2 tails in 2 coin tosses. Okay, I'm going to look at their corresponding decimals. And then I'm going to open this in StatCrunch, which we always do by clicking on when we're in My Lab and Mastering, we click on the little icon that looks like a little spreadsheet. When we click on that, it will open into StatCrunch like this. Here's X, our number of tails, and the corresponding probability for each. We're going to go to the Stat drop-down menu and use a calculator. This particular program, we've got to go all the way to the bottom for these ones and use the one called Custom. Click on that. Now this is our input screen, so we need to tell this program where we've put our data. So we put our values in the column titled X, and we put our weights in the column titled P of X. And then we just hit compute. This here is called the output screen, and the information we're using from this screen is actually down towards the bottom here. Mean is equivalent to 1. Standard deviation is equivalent to 0.707-10678. Let's go back to our notes now. And if you're worried about forgetting those StatCrunch commands, use this to reference. And that StatCrunch program provided us with the mean, population mean, mu, which is equal to 1, which makes sense. If you're going to flip a coin twice, the average or the mean for the count of results that are tails, you'd get 1. It also gave us the standard deviation, rounded to 2 decimal places. Sigma is 0.71. It did not, however, give us 2 other things that were requested from us. It didn't give us the variance or the expected value. No problem. We can find those ourselves. Just take our calculator out. We know that the variance is sigma, and you square it. You always take the standard deviation, you square it, and that will give you the variance. So go ahead and do that. And if you type that in correctly, you should get 0.50 for the variance. And then the last thing we were requested is the expected value. Now, the expected value is always going to be the mean. The expected value of X is always the mean. We're going to use capital E for expected value here, and it is the same as our mean, which was 1. Identifying unusual results. Well, we've talked about unusual results being 2 or more standard deviations away from the mean, and it's the same in this situation here. This is the mean, mu, and if we go plus or minus 2 sigmas, which are the standard deviation. Then we have found the borders for those unusual results. So we call this one, where you add 2 standard deviations, we call that the maximum usual value. And when we subtract 2 standard deviations, we call it the minimum unusual value. I hope this doesn't look completely brand new to you. We looked at it quite a bit, up 1 standard deviation, up 2 standard deviations from the mean, down 1 standard deviation, so z-score is -1, down 2 standard deviations of the mean. And we talked about this right here being the z-scores in what we call the usual range. So the maximum usual value would be 2 standard deviations above the mean, matching this formula. And the minimum usual value would be 2 standard deviations below the mean, matching this formula. Okay, let's practice. Let's identify the maximum and minimum usual values to the nearest tenth for the number of heads in 5 coin tosses. And then we're asked, would it be unusual to get 5 heads in 5 coin tosses? I kind of think it would be. If I flip a coin 5 times to get heads all 5 times, it's not impossible, but I think it might be unusual. So let's find out. The probability distribution table has heads. These are all the X values. If you flip a coin 5 times, you get head 0, 1, 2, 3, 4, or 5. It turns out if we tried to write the sample space out, we would find 32 possible outcomes, one of which gets heads 0 times. 5 of those outcomes would get heads exactly once. 10 of those outcomes would have heads 10 times. 10 out of the 32. 10 of those outcomes would have heads 3 times. 5 of those outcomes would have heads 4 times, and just 1 of them would have heads all 5 times. Here are the corresponding decimals, and we're going to open that in StatCrunch, and that will look like this. Stat menu, open that custom calculator. Input screen needs to know that the values are in the column titled heads, and the weights are in the column titled probability of heads. And compute. Flipping a coin 5 times, we get a mean of 2.5 heads and standard deviation of 1.118034. Back to our notes, we're going to use that information to find the maximum usual value and the minimum usual value. That will be equal to the mean, which was 2.5. And then we're going to plus or minus 2 of the standard deviations. That would look like this here. Type each of those in, and if you type them in correctly, you'll get a max usual value of 4.7 heads in 5 coin tosses, and a minimum usual value of 0.3 heads in 5 coin tosses. So, the question at hand was, would it be unusual to get 5 heads in 5 tosses? The answer is yes, it would be unusual, because the usual range is from 0.3 to 4.7, and 5 is outside of that usual range. So yes, it would be unusual to get heads all 5 times when flipping a coin 5 times. All right, I want you to go ahead and pause the video. Try this example now. Welcome back. Voting in a municipal election is being studied. The table describes the probability distribution for 4 randomly selected people, where X is the number that voted last election. Okay, so 4 randomly selected people, either 0, 1, 2, 3, or 4 of them voted. Corresponding probabilities are here. Looks like these add up to 1, 2, 3, 4, 5, 6, 7, 8. Yep, this right here is a probability distribution. We're asked would it be unusual or not to randomly select 4 people and all 4 of them have voted. I'll tell you a little shortcut. If the probability right here is a number smaller than 0.05, it's unusual. But still going to show you how to calculate it. Okay, so let's open this data in StatCrunch. That will look like this. Stat, calculators, custom. Values are in the column titled X. Weights are in the column titled P of X. Compute. And if you randomly select 4 people based on this data, the average or the mean is 1.45 of them have voted. Standard deviation 1.116, 9154. Back to our notes, that gives us a mean of 1.45, standard deviation 1.116, 915395. We're going to use that information, the mean and the standard deviation, to find the maximum usual value. If we type that in correctly, you got 3.68383079. The minimum usual value, if you typed that one in correctly, you should have got negative 0.78383079. And that means that 4 is outside of that usual range, the ordinary values. That range is between negative 0.7 and 3.6. So 4 would be unusually high, an unusually high number when randomly selecting 4 people and all 4 of them had voted. My name is Emigh. Thank you for being here, and I will see you next time for our discussion on section 5.2, binomial probability distributions.